So in the previous lecture, we studied about statistical mechanics, macroscopic and microscopic properties of the system. We also studied about macrostate and microstate of the system. So macrostate of the system is a state defined by macroscopic properties like pressure, temperature, energy, volume, density, etc. And microstate is nothing but different ways of achieving a particular macrostate. If I talk about classical mechanics, then position and momenta of particles at any instant of time are known as microstates of the system. So in today class, we will study how we can write the equations of motion for our system. So writing equations of motions, uh, if I talk about a simple system, then we can use Newtonian mechanics. But if we have a complex system like a double pendulum, so we use Lagrangian and Hamiltonian mechanics. Lagrangian and Hamiltonian mechanics can also be used to write the equations of motion for a simple system. Now we will see how we can write the equation of motion for our spring mass system using Newtonian mechanics. So let us consider this is a spring mass system. This is a block of mass m and which is attached with a spring over here. So if I apply a small initial displacement in the horizontal direction, so I am going to get a force, a spring force that will act opposite to the direction of acceleration. So if the direction of acceleration is horizontal direction, so the direction of spring force will be opposite to the direction of acceleration, and it is written as kx. So if I draw the free body diagram for our system, so this is our mass and this is the spring force that is acting that to the opposite to the direction of acceleration. So now this is the inertia force I am having. This is mass and this is x double dot is nothing but acceleration. So whenever I apply displacement in the horizontal direction, or when the direction of acceleration in the positive x-axis or horizontal direction, so we always get inertia force opposite to the direction of acceleration of that body. So the inertia force will act opposite to our direction of acceleration in the system. So if I write the equation of motion, so from D'Alembert principle, the sum of all the inertia forces and sum of inertia forces and all the external forces acting on the system is equal to 0. So I will get my equation of motion as mx double dot plus kx equal to 0. Now if I use Lagrangian mechanics to write the equation of motion for our spring mass system, so this is our whole system, and the formula for Lagrangian is written as T minus V, and T is here kinetic energy and V is the potential energy. So T, the kinetic energy, is function of here. You can see here q dot. So q dot is nothing but velocity, so it can also be written as x dot, and this is q, and q is also, or we can also represent q with the help of x. So t and v are the function of, t is a function of velocity and potential energy is a function of position. Okay, as we already know it. So what is L? So L will be equal to the difference of kinetic energy and potential energy. So what is Lagrangian is nothing but the difference of kinetic and potential energy. So here I have written q dot, and here I have written q. So q dot is here x dot and q is here x. Okay, so for a generalized coordinate q, if I want to write the equation of motion, so we will write like this, dy dt of dou L by dou q dot minus dou L by dou q equal to 0. So first I will calculate dou L by dou q dot. So this is my value of L written over here. So when I find its partial derivative with respect to q dot, I will get mq dot. And in next step, I will find its derivative with respect to dt. So when I find its derivative dy dt of dou L by dou q dot, then what I will get is mq double dot. And after that, I will find the value of dou L by dou q. So when I find the value of dou L by dou q, what I will get is minus k q. So after that, I will put these two values in the equation written over here, and I will replace q double dot, that is acceleration, with x double dot, and q, I will replace q with x. Okay, so when I will put all these two values in this equation, I will get the equation of motion for our spring mass system using Lagrangian mechanics. So now we will write the equation of motion using Hamiltonian mechanics. So this is our spring mass system. So to write the equation of motion for a generalized coordinate q, or we can say x, we have Hamiltonian equal to, so it's q dot p minus L. So what is q dot here? So it is velocity, which I can also write as x dot. And what is p here? So p is a momentum here, which is nothing but mass into x dot, that is velocity. So momentum is mass into velocity. So if I put the value of q dot as x dot, write the value of p as mx dot minus L. So L is nothing but Lagrangian here, and this is the formula of Lagrangian. So I will replace q dot by x dot, I will replace x, q by x, and put this value in this formula. And after solving it, I will get h equal to half m x dot square plus half kx square. So 1 by half mx dot square is the kinetic energy of the system, and half kx square is potential energy of the system. So what is Hamiltonian? It is the total energy of the system. So to write the equation of motion for a generalized system, it can be written as, so q dot equal to dou h by dou p, and p dot equal to minus dou h by dou q. So here you have to remember that q dot is nothing but velocity, which can be written as x dot, and p is here momentum, which is m into x dot, or mass into velocity. So I will replace q dot with x dot here, and dou h by dou. So I will write the value of p as p is the momentum. So momentum is mass into velocity. So m mass into x dot is velocity. So mx dot. So when I will find its derivative, so this is Hamiltonian h written over here. When I will find its derivative with respect to mx dot, so I will get x dot. And in the second part, I have the derivative of momentum. So momentum is mass into velocity. So when I find its derivative, so it will come out as mx double dot, and it is equal to the the partial derivative of uh, dou h upon dou q. So this is h, and when I find its partial derivative with respect to q, then what I will get is minus k into x. Okay, as q is x here, q is x here, so what I will get, minus k into x. So when I will write it, then I will get the equation of motion as mx double dot plus kx equal to 0. Thank you.